Okay, so first let me remind you what's coming up. So next Thursday is exam 2. And the topics for that, so we started circular motion last time, but none of that is going to be on there. It's just up through Newton's laws.
I got.
And remember, remember that all the exams in this class start, like, everything is possible for the exam. So go back to the beginning. Everything's cumulative for the quizzes, the exams, the lab exams, okay? So what I would recommend doing to get ready for the exams is go back, like really, I think you can think about these exams as kind of just about the daily problems, you know? And if you can get to the point where on every daily problem, you know how to do it, you could answer questions to somebody who didn't know how to do it. Why did you do this and that? Like if you understand the thought process on each of those problems, then you'll ace the exam, you know? So that's what you're trying to get to. And I would say, go back to this beginning of the problems and just look at the problems and just ask yourself, do I know the steps to doing this? And if you look at one and the answer is yes, you do this, 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 then don't worry about that one anymore. Go on to the next one. And wait till you get to the ones where you're a little hazy on it and spend some time reminding yourself how to do those. And that's just a way to make sure you've covered everything without, like, obviously, like, it's a lot to ask to go through every single problem and do it again. But I think that's a reasonable approach. And then, so that's the exam. Anybody have any questions about the exam? Okay. And then the week after that is lab exam 2. So that's the week of, I think it's 11/6 is the Monday to 11/10. And the topics for that are everything we've done up through this week. So up through this week's review lab. I was going to say something about this. Oh, I know. I just put up all of the lab worksheets on D2L, so in the content section. So if there's any you lost or whatever, you can pull any of those up, print them up. But the questions, just like with the first lab exam, are going to be very similar to the questions that you've answered in the labs. So if you remind yourself how to do that stuff, everything should look familiar. Last, on exam 1, I think most people were done, close to done in half an hour. It's probably going to be similar to that. I mean, it won't be more than an hour for sure. I mean, maybe it'll be 45 minutes or something. You have the whole time to work on it, but I don't think anyone will really need that much time. Anybody have any questions about the lab exam? Okay. So before I go on with new stuff, anybody have any homework questions you want me to go over? Yeah.
Can you just go through A on number 1?
Yeah, for sure. So that's the one. Do you have it in front of you? That's,
Really?
okay, I'll get it. But it's circular motion number 1. And it gives you a circle. It tells you the radius of the circle, and there are 4 points. And basically, you're just going through the same steps 4 different times, just trying to ingrain this process. It works best for ingraining this stuff if you treat it like you haven't done it 3 times before, you know what I mean? Like, do each one individually. Don't try to just say like, okay, I'm gonna adapt this to the next one. Go back to, at each new point, go back to the beginning, go through the steps, go through the free body diagram. Okay, so let me pull this up. While we're here, so here's where the lab worksheets are. Lab handouts at the bottom. Problems. Okay, so this mass is 100 kilograms, and it's moving counterclockwise. It doesn't actually matter that it's horizontal to the ground. Nothing, that doesn't come up in any way. 100 kilograms, radius of 20 meters, speed of 5. And A is down at the bottom. Okay, so at this point here, we know that this is, I already forgot, 5 meters per second, 20 meters. That's a big old circle. Okay, so 20 meters. The mass is 100 kilograms. It's going counterclockwise. And the speed is 5 meters per second. And let's calculate the velocity vector, the total acceleration vector, and the net force vector. Okay, well, is this a tetherball problem? Not that we know. It does say that it's constant speed, the motion, which means that we're not going to have any tangential acceleration. Okay, tangential acceleration is like our A parallel with general two-dimensional motion. It only is non-zero if the thing is changing speed. So since it's not a tetherball problem, I'm going to use the approach that we talked about last time. So this is the point. Our coordinate system is here. Centripetal acceleration is going to go toward the center. The magnitude of the centripetal acceleration is the speed squared over the radius of the circle. So that's 25 over 20, which is 1.25. You can see from the drawing that that's in the positive y direction. So the centripetal acceleration as a vector is 0, 1.25. Now, the total acceleration is always the centripetal plus the tangential, but like I said, this is constant speed, so there's no tangential. So this is the total acceleration vector. Okay, what about the velocity vector? I don't think it actually asked for that in the problem, but let's figure it out. the velocity is always tangent to the path in the direction of motion. So the velocity is like this. From that picture, you can see it's in the positive x direction. The magnitude, the speed is 5 meters per second. So this is going to be positive 5 in the x direction, 0 in the y direction. And now the final thing that we have to figure out is the net force on this object at that point. I think I've said a few times, whenever you're going to use Newton's second law, you need to draw a free body diagram. There's one exception to that, and that's if the force that you're dealing with is the net force. Because the net force doesn't show up in a free body diagram, you only put individual forces in there. And if you did put it in a free body diagram, it wouldn't help you at all. So I'm just going to go, anytime you're dealing with the net force instead of individual forces, you can just jump right to Newton's second law. So Newton's second law says the net force is equal to the mass times the acceleration, which in our case is 100 kilograms times 0, 1.25. And so multiply that out and you get 0 for x, 125 newtons for y. And if you want to visualize that, that's 125 Newton force in the positive y direction. Any questions about that? Any other homework questions anyone wants to see? I think maybe that's the only one that's been assigned so far, right? Okay. So going back to the new stuff, I said that we're dividing up circular motion into 2 categories. The first one is not a tetherball problem. And the second one is a tetherball problem. Well, you're going to use the first category a lot more often, you know, but it turns 2 L's in tetherball. We've talked about this one, and so we still have this one to do. And the reason that I'm doing this one separately is it turns out there's a quicker, more efficient way to do this calculation. You could kind of work your way around what you want to calculate using the other approach, but it's just going to be a lot easier to do it this way. So, okay, tetherball problems. One thing to remember about this is, well, first let me describe what it is. So this is any circular motion that's parallel to the ground where the only contact with the body is a cable. Okay, so that's like the definition of what we're talking about. It doesn't actually have to be a tether ball. It doesn't have to be a ball. It could be an elephant glued to a chain that you're swinging around or whatever, you know. It would have to be really good glue, though. So be careful with that. But so here, like this would be a tether ball problem. You know, imagine you have something hooked to the ceiling. and you have your mass here, whatever that is, and it's going around in a circle like this. Okay. What about oh, your nose is funny today. Okay, so what about a circle going around like this? The only contact with that mass is a string. So, but that circle isn't horizontal. It's not parallel to the ground. So that's a different kind of thing. You wouldn't use this approach. So this is not a tetherball problem. This you want to use the other approach for. Okay? And what else? This is another one that's almost a tetherball problem, but not quite. What about if you had a thing moving around a horizontal circle like this on a string, and this ball is like sliding on ice or rolling around as it goes? Well, this is a circle that's parallel to the ground, and it's connected to a cable, but it's also in contact with the ground. So you wouldn't use this approach there either. It's not even the friction that does it. It's just the fact that there's a normal force. But any force besides the cable isn't allowed. So we're talking about this, but not either of those. And one thing to notice about this, and one of the reasons that this different approach is so useful, is tetherball problems are always uniform circular motion. They never have a tangential acceleration. Tetherball problems are always uniform circular motion. So what that means is the total acceleration vector is the centripetal acceleration vector. And for these kind of problems, here are the steps you want to take. So first, remember the first step for non-tetherball problems is to choose a view where you can see the circular motion. Choose to look at it from a plane where the circle is visible. Here you don't do that. Here we're going to take a side view of the problem. So in the first step, we're treating this differently. Second, draw. Now things get pretty similar to the other approach. Really the one major difference is taking a different view of this problem, putting your coordinate system in a different plane. So now draw an arrow from the mass toward the center. That's your centripetal acceleration direction. The magnitude of the centripetal acceleration is v squared over r. But now, if I draw like a tetherball kind of setup, if this angle is theta. And that's never going to be straight out in a tetherball problem. That would take infinite speed. Okay, the faster that ball is going, the closer that that cable is to horizontal. That makes sort of intuitive sense, right? But you never get to horizontal. You just get closer and closer. This R is equal to the length of the cable times the cosine of that angle. So this right here is the radius of the circle. And then once you've done this, you know the centripetal acceleration vector. Now you can draw a free body diagram and use Newton's second law with your total acceleration just equal to that centripetal acceleration vector. Okay? So let's do a problem. I'm going to do it twice, which sometimes gets sort of boring, but I just want to show. So I'm going to show the setup, and I'm going to show you can think of this thing on the left side of the pole or the right side of the pole, and everything will work out the same if you do your vectors right. So let's say that we have, okay, so here's an example. And let's say that the mass of the ball is 0.1 kilograms. And the angle the cable makes with the horizontal is 45 degrees. And the length of that string is 0.25 meters. And we want to calculate the cable tension, so how hard that cable is being pulled by the ball, and the speed of the ball. Does it make sense that that t would have to be something that we calculate? Does that make intuitive sense to you? Like, I think maybe some people would look at that and think like, oh, well, the tension in the cable is just the weight of the ball. But it doesn't work like that. You can imagine, I mean, if you imagine kind of a flimsy string holding a mass, and if you start out going really slowly, maybe, the string is fine, but as it goes faster and faster, eventually that string is going to break. So the tension in that cable depends on the speed of the ball. And the speed of the ball and the angle are related to each other. Okay. Okay, I'm going to do this two ways. So the first way, I'm going to take a view where, so here's the pole. The ball is over on the left side of the pole. So this angle is 45 degrees. I'm going to use a coordinate system like this. The centripetal acceleration vector is straight to the right, because it's toward the center of the circle, and this circle is even though the cable isn't horizontal, the circle is horizontal. Do you see that? Okay, well, the centripetal acceleration vector's magnitude is v squared over r. And r is the length of the cable times the cosine of 45 degrees. So 0.25 times the cosine of 45 degrees. And if you punch that in, you get v squared over 0.177. The centripetal acceleration vector that we drew is in the positive x direction. So as a vector, the centripetal acceleration is v squared over 0.177, and then 0 for y. And since there's no tangential acceleration, this is also the total acceleration. Okay? Well, now we have the acceleration. So now we can go to a free body diagram. There's a weight force straight down that's equal to the mass times 9.81. So 0.1 times 9.81 is 0.981. And then the only contact is a pulling force that's parallel to the cable away from the body. I'll call that T. Okay, so what are the components of that force from that cable? If you draw the coordinate system and put the tail at the origin, the magnitude of this is T. This angle is 45. So that force vector is just T times the cosine of 45, T times the sine of 45. Which comes out to be like 0.707 T, 0.707 T. And now I'll go to Newton's second law. We have the weight force of negative 0.981 plus the force from the cable, 0.707 T, 0.707 T. That's all the forces. That's equal to the mass, 0.1, times the acceleration vector that we figured out before. So that's v squared over 0.177, and then 0 for y. So we have two equations. The x equation says 0.7071 T is equal to so I took 0.1 divided by 0.177, and you get 0.56 v squared. And then the y equation says negative 0.981 plus 0.707 T is equal to 0. So that's just a system of two equations for two variables. you can solve the y equation first to get t, and then plug that into the x equation. So this says 0.707 t is equal to 0.981. And so t is equal to 1.39 newtons. And then plug that into the x equation. And you get 0.707 times what we just found, 1.39, is equal to 0.565 v squared. So v squared is equal to 1.74. Take the square root of both sides and you get v is equal to plus or minus 1.32 meters per second. This is a speed, so negative doesn't make any sense for a speed, so we want the positive one. Any questions about that? Yeah.
How did you do the algebra for 0.565 squared?
Yeah. Right. I mean, you don't have to do it for one thing. Like, you could leave it as 0.1 v squared over 0.177 and then divide both sides by whatever and multiply both sides by the other. But what I did is I thought of it as just a single number multiplied by v squared, and that single number is 0.1 over 0.177. And so I just did 0.1 over 0.177, and that's what it is.
Oh,
Yeah.
So how you get the 0.1?
That's the mass that was given in the problem. And so this is Newton's second law, and that's the mass of the object. Any other questions? Okay. So I said I'm going to do this 2 times. So same problem, but let's think about the other view instead. You never have to do this, but you could. The way I did it is a little simpler. But so let's say that the view we want is this way. So this angle is 45 degrees. And our coordinate system is still like this. The centripetal acceleration is toward the center of the circle, so this way. The magnitude of the centripetal acceleration is v squared over the length of the cable times the cosine of 45. And so it's the same as it was before, v squared over 0.177. But now to get the vector, you can see from the picture that this time the centripetal acceleration is in the negative x direction. So this is going to be negative v squared over 0.177. And then 0 for y. And since it's uniform circular motion, this is also the total acceleration. So this time we have this negative x component. Now go to the free body diagram. And you have the weight of 0.981. And a cable force T going that way. So let's think about the components of the force from the cable this time. So there's the coordinate system. Our force vector is like this. Where this angle is 45 degrees. So this time that force vector is going to be t times, so what's the angle to go from the positive x-axis to the vector this time? 135. So this is going to be t times cosine of 135, t times sine of 135. So now we get negative 0.707 t, positive 0.707 t. Newton's second law says 0, negative 0.981 plus negative 0.707 t, positive 0.707 t is equal to the mass times the acceleration. So in this case, the acceleration is negative v squared over 0.177, and then 0 for y. And now you get these two equations. Negative 0.707 t is equal to negative 0.1, well, again, this comes out to negative 0.565 v squared. The y equation says negative 0.981 plus 0.707 t is equal to 0. And now these give the exact same answer we got before because those two negative signs cancel out. So all this shows you is you could do this problem with by imagining the mass on either side of that circle, and you'll get the same answers. It's a little easier. You just don't have to deal with the angle greater than 90 degrees and the negative signs and stuff if you do it on the left side. Any questions about that? Okay, let's say, well, let me just give another one and let you work through it. So let's say we have a mass of 10 kilograms on a chain with a length of 0.8 meters. And let's say that the angle between the chain and the horizontal is 20 degrees. What are the cable tension force and the speed of the mass? Okay, so take a few minutes, look back at the example I just did and see if you can work through this, and feel free to talk to each other, compare stuff as you go, ask me questions as you go, and then I'll go through it after I give you a little time. Okay, so the first thing you have to do is choose a view, and I'm going to choose the easier one where it's over here, but if you choose the other side, you'll get the same answers if you do it right. This angle is 20 degrees. And my coordinate system is the normal coordinate system. The centripetal acceleration is this way. The magnitude of the centripetal acceleration is v squared over 0.8 times the cosine of 20. And that comes out to be v squared over 0.752. It's in the positive x direction. So the centripetal acceleration vector is positive v squared over 0.752 for x and 0 for y. And that's the total acceleration vector because there's no tangential. And now we can go to a free body diagram since we have the acceleration. You have the cable force and the weight. The weight is 10 times 9.81, so 98.1. The force from the cable, to get the components for that, it's put the tail at the origin. And the angle is 20 degrees. So you have t times the cosine of 20 degrees, t times the sine of 20 degrees, which is 0.940 t, 0.342 t. And now Newton's second law says 0, negative 98.1 plus 0.940 t, 0.342 t is equal to the mass, 10 kilograms, times the acceleration vector that we figured out before. So that's v squared over 0.752 for x, 0 for y. So we get these same familiar two equations. They're always going to look something like this. 0.940 t is equal to, so I'm going to do 10 divided by 0.752. And so what you get for that is 13.30 v squared. And for the y equation, you get negative 98.1 plus 0.342 t is equal to 0. The y equation says 0.342 t is equal to 98.1. And so you get t is equal to 286.84 newtons. I mean, notice that's a lot bigger than the weight of this thing is only 98.1 newtons. So, 200 of the majority of this is coming from the force required to keep this in circular motion. And now we can take that t, plug it into the x equation. And we get 0.940 times 286.84 is equal to 13.30 v squared. So v squared is equal to 20.27. Take the square root of both sides and you get v is plus or minus 4.50 meters per second. And we want the positive because it's speed. Any questions about that?
I got a different for t cosine, because I was doing that in the negative direction.
Okay.
T cosine of 160, and I got 3.42 t for that, not 0.342. And I don't know how I'm off by that.
No, that's what I got. You're not off. I just have the 0 in front of the decimal.
Oh, okay.
Yeah, that's right. I mean, you should have you got a negative point.
Yeah.
Right.
But I got 3.42.
Oh, you got 3.42. 3.42. When you did.
I still got the correct velocity, but I didn't get the correct tension.
Okay. So let's see. Let's see what happened there. So like up here, when you did your, when you calculated that force,
Yeah.
you had t times cosine of 160 and sine of 160. I think you just wrote it down wrong. I mean, I think your calculator gave you negative 0.94 and 0.342.
Because I got the same x. I just think it's
Same x. Okay, yeah, right.
okay. Sounds good.
Yeah. Remember that for any angle, the cosine squared plus the sine squared has to be equal to 1. So, so you can't ever get a cosine or a sine that's bigger than 1, no matter what angle you choose. So, I bet you just looked at it and just wrote down the wrong thing. Any other questions?
For the square root, do you want us to write the positive?
I don't care about that, but I do, in general, you should be careful about just remember when you take the square root of a variable, you always have a plus or minus answer, and you need to somehow determine which one it is. Yeah. Okay. I want to do one more problem because it's going to come up when we do conservation of energy. And this is the first time that we could do this calculation. So let's say that you have, so there's kind of two identical ways to think about this problem. One is a mass on a string that you're swinging in a circle like this. And the other one is like a little cart with wheels that you're rolling up a loop-de-loop, you know? And really you think of it exactly the same. Let's do the cart thing. So Okay, so let's say that this cart is going around, we're trying to get this cart to roll all the way around this loop. Okay. Let's say that the mass of the cart is 0.5 kilograms. And the radius of this loop is 0.5 meters. So the whole thing is a meter. This whole loop is this far, you know, that's the circle. So you got to get this thing going pretty fast to make it over the top. And what we're going to calculate is what's the slowest the cart can be at the top, you know, what's the slowest speed, you know. The cart can have at the top of the loop to make it around. This is also a good snowboarding question. I mean, it might be sort of a pain to make a loop out of snow like that. I don't know, but okay. So is this a tetherball question? No. So we're going to use that sort of general approach, and let's think about a couple of things before I start going into the whole approach for circular motion problems. First of all, you saw this in lab in one thing. For a thing under the influence of gravity like this, it's slowing down on the way up. It's speeding up on the way down. Is it slowing down or speeding up at the top and the bottom? Neither. At those two instances, it's not changing speed because it's not changing height. Okay? So when we do this calculation up at the top of the circle, there's not going to be any tangential acceleration. Okay? So here are the two facts we're going to consider. At the top, this would also be true at the bottom. The tangential acceleration is 0. The other fact is, so what does it mean for this to be going as slowly as it can possibly go and still make it around the circle? What that means is we're going to assume that it continues the circle and figure out what force has to be applied by the ground, by the loop, in order to continue that circular path at these different speeds. If this is going faster than it needs to go, the ground is going to have to push it down to keep it in the circular path. If it's going too slowly, you still could say, okay, it makes it around, but it's going to say that the ground has to pull up on it, which really wouldn't happen. It would just fall off. Okay? So at that exact moment where it's at the minimum speed it can have to make it around the loop, that contact force is going to be 0. So that's the criterion we're going to use. We're going to assume this is circular motion, require that that contact force is 0, and then figure out the speed. Okay? So that's the first fact, is that tangential acceleration is 0. At the slowest speed that maintains this circular motion, the normal force pushing down on it is going to be equal to 0. Okay, so to do this problem, it's not a tetherball problem, so we're going to use a view where we're looking at the circular shape. So here's our view. The point that we're going to do this calculation is up here at the top. The centripetal acceleration vector is this way. The magnitude of the centripetal acceleration is v squared over r. The r is 0.5. That's the radius of this circular path. Now combine that magnitude with the direction in the negative y direction, and you get that the centripetal acceleration vector is 0 negative v squared over 0.5. Since there's no tangential acceleration at this instant, this is also the total acceleration. Okay, so now we'll go to the free body diagram. And we're thinking of this cart when it's at the top, so like the outline would look something like this. The weight force is acting down. It has a mass of 0.5 kilograms. So 0.5 times 9.81, this force is 4.905. And then the ground is pushing on the wheels. The rule for a pushing force is perpendicular to the surface toward the chosen body. So this is the force that the ground, not the ground, but the loop is pushing on the wheels, is applying to the wheels. But we already said that this is going to be 0.
If it was on the side or any other point on the top bottom, it would be 0.
If you'd have to think about what it meant, what would it mean? It doesn't really occur to me what that would mean. But in this case, what it means is that it's exactly at that middle point between, if it's going to complete that circular path, that middle point between the ground having to push to keep it in a circle or it would like launch, or pull where if the ground wasn't there, it would just drop off, you know? So that's what it means at the top. Okay, so now Newton's second law. Since this n is equal to 0, the only force that shows up is 0, negative 4.905. I guess maybe I'll write in, this 0 force for the pushing force, but obviously that doesn't do anything to the equation. This is equal to the mass, 0.5 kilograms, times the acceleration that we calculated. So 0 for x, negative v squared over 0.5 for y. And you get two equations. X says 0 equals 0. Y says negative 4.905 is equal to, this is just by the values I picked, the 0.5s cancel out. So this is equal to negative v squared. So v squared is 4.905. V is the square root of that. Uh, 2.21 meters per second. So for this size circle, that thing has to be going about 5 miles per hour at the top, or else it's gonna fall off the loop. And, you know, it doesn't occur to you right away that this is true, but like I said, this calculation would look exactly the same if instead of this thing like sliding or rolling along this ramp, it was being swung in a circle by a string. You'd still have this case where instead of this being a pushing force, it would be a pulling force that you would set equal to 0, and you'd get the exact same values. Okay, so partly that's an example of a circular motion problem, a little more practice. Partly that's something that we're going to do again when we do conservation of energy. We'll use this again. Okay, that's all.